Okay, so we're digging in on number 2 and 3. So we have a massive car moving down a 10-degree slope, and the driver hits the brakes. Net force acting on the car is -2 times 10 to the 4th newtons. Coefficient of friction is given, and we want the mass. So the issue that people are having, we know that F net equals MA. We can all agree on that. No issues there. So we know that whatever the sign on F net is going to be the same as the sign on A, because the acceleration will be in the direction, this is a vector, of the net force. Yes? We're good so far. So if we call this negative and this positive, and we realize that this car, and I'm going to move the car here, is moving down slope, but its velocity is decreasing. And I'm going to draw this in red. So its motion is this way, but let's say its initial velocity here is 10, and its final velocity here is 0, or 1. It could be slowing down, it could be, we say it's coming to a stop. So what's the acceleration over that interval? Positive or negative? Negative, because it's slowing down. So if the acceleration going that way is negative, and the net force is negative, we have a problem with the fact that they give us a negative number for this rather than a magnitude, and we're applying other labels to it. That's the issue. So despite the fact that I'm attached to the Cartesian coordinate system, I got to let go of it here, because or I have to redraw this like this. So this is my negative direction and this is my positive. I don't know why I always draw slopes the other way. I just do. I'm like physically incapable of drawing a slope this direction. It freaks me out for no rational reason. So now if I do it this way, this aligns the signs that we're using with the image that I have, because the motion is this direction, the acceleration is that direction, the net force is that direction. It means friction's winning over gravity because this thing is coming to a stop. So what does that mean in terms of my sum of forces? Well, it means that on the x-axis, sum of forces on the x equals F net. And I'm going to drop back to that little trick that I used to do with just sum of forces in 4A. Do you remember 4A when life was easy and we didn't have to think about anything moving and you just added stuff up? Oh my gosh. I'm going to do that. And then I'm going to do the other stuff that's on this axis. So I'm going to do Fk, and of course Fk is in the same direction as net force. Oh, so then I need to, wait. Okay, hold on. I got Fgx and I got Fk. Without putting in any plus or minus signs, without assigning signs, Fk is this way, f of gx is that way, yes? We all agree. So if I'm going to be consistent with the Cartesian coordinate system that I've established here, and the fact that they gave me a negative see, this is the problem. They gave you a negative magnitude for net force. Ugh. Because here's what we're doing. We're saying, okay, well, that means it would be f of gx minus fk. And then fk is negative. Well, then we say, okay, well, the net force is negative. But they gave you a negative number, and two negatives make a positive. If we ignore the fact that they assigned a negative to the net force, we're fine trusting the signs on our variables. The fact that they wrote it, they should have written the magnitude of the net force is. If I was to rewrite that problem, that is what I would do. Because if the magnitude of the net force is the 2 times 10 to the whatever, it's fine, because we're consistent with our signs internally. If we use their negative sign on our net force, it flips everything for us because we're putting a negative number in with something that we say should be a negative. Does this make it better or worse? Okay, so to continue to try to clarify this and see if we hopefully don't make the water any muddier. Yes. So the question was, we want our mass to be positive if our acceleration is negative and our net force are negative. Why is this an issue? Well, it's not, except we don't have a value for acceleration. We're just using net force, and we're getting our value for mass out of here, because this is, of course, mg sine theta. So we're given a value, we're given a value for net force, and we're given a value, well, we're given a means to find an expression for Fk. We're not given mass. So let's go ahead and plug some more stuff in and see how this all shakes out. Okay, the reason we have a problem is because when we set it up like this, so net force equals mg sine theta minus Fk, we don't have a negative sign in front of Fnet. Now the value we're going to plug into Fnet is negative. But if we're trusting the algebra from here before we plug in a value, we want Fnet should be negative if Fk is negative, because we've established that they're in the same direction. I saw one light bulb go on. Do I see any other flickers? So if we use this, which is correct according to the situation that we're describing here, where Fnet and Fk are both going to be upslope and hence negative, well, if we plug a negative number into negative Fnet, now we have a positive and our signs are wrong. Does that help? Still no. Okay, a few people, yes. We're going to, because I think maybe not more than one person is having a sort of philosophical, intellectual struggle with the concept that it's still moving, but its acceleration is negative. When we introduced in two-dimensional motion the concept of velocity versus acceleration, you can have a positive velocity with a negative acceleration, which means you're slowing down. So remember that if we have a velocity time graph, position time graph, this is positive velocity, that's negative velocity. But if we have a velocity time graph, the slope of that is acceleration. These are all values that are above 0. This is all positive velocity. Velocity doesn't get to 0 till here. It's still moving, but its velocity is approaching 0. As its velocity approaches 0, its acceleration is negative. Does that help?
No, that the acceleration.
So let's, I'm going to pause here. Okay, so we're down to just a couple, so we're going to go take this to paper and just kind of work together.